When we study electromagnetism, one of the most important principles you'll run into is Gauss's law, which relates behavior of the electric field at a given point to the charge density at that point. Now, to use Gauss's law in general is very difficult. It always applies, it's always true, but in most situations, almost all situations, it's really complicated to go from Gauss's law to determine what the electric field in some region is. But there are three special situations, three special configurations of electric fields where the mathematics of Gauss's law simplifies enormously, and we can take advantage of Gauss's law then to solve and find the electric field in the most easy way you can imagine. Those three special cases are the cases of unidirectional, axial, and radial electric fields, which I'll define shortly. But those are these three special cases. In those cases, Gauss's law becomes a powerful computational tool, not just in principle, but in practice, to figure out what those fields are. Now, each one of those cases is the result of a charge distribution that has a special symmetry. And so what I want to do today is to talk about those three special symmetries of charges and how we can reason from symmetry to put constraints on what type of electric field we can have. This is actually a really useful and broadly applicable tool in physics. Even if I didn't know Gauss's law, even if I don't know the principles of physics, as long as I know that electric charges give rise to electric fields, I can use symmetry reasoning to figure out a lot about what those electric fields can look like, even without knowing the physical laws at all. There's a sense in which this pure logic of symmetry is a more powerful principle than any law of physics you'll ever learn, because it's pure logic. It's mathematical reasoning, logical reasoning that is independent of the exact rules that you use. So this is a great example of symmetry reasoning in physics, and it's useful for recognizing cases where you can apply Gauss's law in easy ways. So here's what I want to do. I want to go through, I'll start with a unidirectional field, and I'll talk about the charge distribution that gives rise to that. In particular, for a unidirectional field, the charge distribution involved always has what's known as infinite plane symmetry. Infinite plane symmetry means that, visually speaking, I've got some infinite plane. I'm just drawing a little segment of it. It goes off in all directions. And it's an infinite plane, and the charge is evenly spread at all places along that plane. So you think about a perfectly infinite plane. What's true about that? Well, this point and this point, if I move back and forth, are the same. If I rotate around the plane, if I sort of zoom around from side to side, it looks the same. An infinite plane is pretty featureless. What's that tell me? Well, what I'm going to do is I'm going to talk about coordinates on this. And by the way, it doesn't have to be just a plane. We call it infinite plane symmetry or planar symmetry. But if I had a thick slab that was infinite in all directions and that was uniform from place to place, that would be the same thing. So I'm going to describe this with coordinates. It's always natural to talk about coordinates in physics. And so I'm going to define coordinates. I'll just use the standard x, y, and z. And the way I'll do that, up in my infinite plane here, I'm going to define the z direction to be orthogonal to the plane, so coming up out of it. And I'll choose x and y to be in the plane. So the z direction is perpendicular, orthogonal to the plane, x and y are in the plane. Those are the coordinates we're going to use. And now, just based on that, assuming that the electric charge is evenly distributed, uniformly distributed across this plane, we're going to figure out what we can say about the electric field direction based on symmetry. Well, electric fields are going to come in general, an electric field is a vector. It has an x and a y and a z component. That's what vectors do in 3 dimensions, if our coordinates are x, y, and z. And so, in general, I'm going to say, at some point above the plane, I've got some electric field going in some funny direction. Here's where the symmetry argument comes in. Imagine what would happen if you looked at the electric fields and the charges here, and I smiled and pointed, and then you turn your back. And while your back is turned, I rotate the whole plane by 17 degrees. Whatever. I rotate it by some angle, but I don't tilt it or anything. I just rotate it around the z-axis. You turn around and look back. What do you see? The charges should look exactly the same to you, right? The positions of all those charges haven't changed. But the electric field up above, if it had been at some angle like this, it would have rotated to some other angle. That wouldn't make sense. If we know that electric charges produce electric fields, then it had better be that if the charges look the same, the fields will look the same. So based on rotational symmetry, rotations around the z-axis, based on those rotations, we know that Ex equals 0 and Ey equals 0. Because of rotational symmetry, we know that the x and y components of that have to be 0, because if there were any x-directed thing and we rotate, it would change. It would turn into a y component instead. So we know that means that the electric field has to be purely in the z direction. So the electric field vector is equal to, and there are different ways people write this. Some people will write E sub z times z hat, meaning that our field is some number times the z hat unit vector. Other people might write this as a column vector, saying this is 0, 0, E sub z. However you want to write it, that's our constraint on what the field shape will be, on what the field will look like. It's all in the z direction. Now, if we happen to know that a lot of times an infinite plane has a further symmetry principle that says that it is that if you reflect it top to bottom, if you flip it top to bottom, it will look the same. We might not require that quite so strictly because unidirectional fields are a bit more general than that, but if you have that principle, if you have some center line, central plane rather, where flipping top to bottom is true, then you would find that if I had an electric field that went away from the plane up top, and I flipped it top to bottom, so it was a plus z here, then on the bottom it would be down. So in particular, this field configuration wouldn't work if we were plus z on both sides, because if I flip it and the charges look the same, the fields would flip. So if we have a center line, if it's symmetric around z equals 0, if there's reflections across z equals 0, which is optional, if that's the case, then either always away or always toward the plane are the only possible fields. It's away above and away below, or toward above and toward below. So those are the only possibilities. If reflections across, if that's a symmetry, then I guess we're either, then the result is this is always toward or away from that plane, from that central line, that z equals 0 point. The other thing we can do, at this point we know it's all E sub z, there's only a z component, but we haven't said anything about how this depends on the coordinates, how that strength, E sub z, how that depends on the three coordinates x, y, and z. And there, we can add this extra piece. We can ask about the coordinate dependence of our field. And in this case, well, we can say, okay, no, it's only E sub z, but how does that change? Well, again, imagine you look at this, and I have my field configuration, you turn your back, and I just slide this horizontally by some distance along the x or the y direction or some combination of those. And then you look back. What do you see? The plane looks the same to you because it's infinite, right? There aren't any edges. So if I've shifted it by 17 centimeters to the right, I'm big on 17 today. If I've shifted it by 17 centimeters to the right, you're going to look and see the same thing. It had better be the electric fields haven't changed either. So sliding something, shifting along some coordinate is technically called translational symmetry. So if I look at translation along x or y, because there's translational symmetry along x or y, I can say that this is independent of x and y. The result can't depend on the value of x and y, since I can just slide that a little bit and you won't notice the difference in the charges. As long as the charge distribution looks the same, the electric field should look the same. So I guess maybe I didn't leave a place for this. Let me just summarize in here then my electric field in this case. My electric field has to be some z component, E sub z, that's only a function of z in the z hat direction. And that's my result for unidirectional fields. And that's why it's unidirectional. It's all in the z hat direction, and it only depends on the z coordinate. If we have that reflectional symmetry, it will only depend on the distance from that center plane. So okay, we've got that. That's our unidirectional symmetry. Next, and you can see how we got that, right? We got this. We got to this very specific value of electric field that only depends on one coordinate and only has one component. That's cool. And that was all based on just symmetry reasoning, things that we could do to the distribution of charges that made the charge distribution look the same. So how does that apply to this axial field case? The axial field case corresponds to what's called infinite line. Or maybe I should be more general. Let's call it infinite cylinder. Infinite cylinder symmetry. If we have the symmetry of an infinite cylinder or an infinite line, then a cylindrical symmetry. What's that mean? That means that I have some central axis that's the center of my cylinder, and maybe I'll draw a little cylinder around it, sketch this around, that this goes in both directions. It goes infinitely long in both directions. That's my situation, and if it is truly an infinite cylinder, what we're going to assume is that the charges are evenly distributed in circles around the center. So there's a rotational symmetry that is the same in this case. In this case, I have to talk about coordinates. The natural coordinates for a cylinder, if you've ever studied these, are cylindrical coordinates. And the way I'm going to write cylindrical coordinates are S, phi, z, where the z direction is going to be, let me draw this on here, my z direction is going to be along the axis of the cylinder, and S will always be the distance away from the axis, the distance from a given point to the closest point on the axis, and the phi direction will go around the cylinder. And have I done that backward? Yes, I've done that backward. The phi direction, if I want to be really careful, the phi direction should go the way the right-hand rule would tell me. Guess I should have done my cylinder the other way. Whatever. The phi direction goes around the cylinder that way, so that so phi is the rotational direction around the cylinder. So, okay, that's my idea of these cylindrical coordinates. And the reason I've written it this way is, remember, when I've talked about this infinite cylinder symmetry, the idea is that rotating this shouldn't change anything. That'll actually lead us directly to the constraints on the electric field direction. I should have put this a little higher, shouldn't I? Just to have more room. S, phi, z. Constraints on the electric field direction. I can look at this. Let's think about it. Imagine, for example, that I had an electric field that pointed around the cylinder at any given point, that pointed in some direction that went around the cylinder. Let's say it went. Let's say that it went in some circling way around. If I do that, then you can imagine. First of all, I'm rephrasing this badly. Let me start again. In this case, rotating isn't going to tell us much. It won't actually wind up telling us a lot about how this works if we talk in these coordinates. If I had just an x-directed field, for example, I'd have a problem, because if it was in the x direction, and I rotated, it would suddenly look like it was in the y direction instead. But that's a different position. It's a little hard to track. So what we can argue, the best argument here actually turns out to be based less on x, y, and z and rotations, but based more on some of these reflectional symmetries we've talked about. Let's think about that. Let's say I had a direction that was going around the cylinder this way, something coming out in that x direction or phi direction. And let's imagine now that I reflect, you turn your back, and I just flip this whole thing around the other way, so that I've swapped x and minus x, and I've reflected across a central plane, across a mirror through the middle of this thing. If I do that, then I'll find that the field that was going like this ought to reflect and go into the board now. If I just reflect across the plane of the board here, a field that was coming out will go in, but you would notice a difference in that. You wouldn't notice a difference in where the charges were, because we can reflect this whole line, reflect it front to back, or we can rotate it around 180 degrees if you want to think of it that way. Because we can do that, that means nothing could be going into and out of the board. There can't be any electric field that goes around this cylinder. So we can say reflect across the center, or maybe a diameter or something. How do I want to phrase that? Reflect across, I'll say, a center plane. That tells me, that reflectional symmetry means that there's no phi hat. I guess if I want to write it as that there's no electric field in the phi direction, no Ex or Ey. There can't be. I can't say no Ex or Ey. I'll talk about phi direction. There can't be anything that goes around this thing. There can't be anything that goes around the cylinder. There can't be anything around the cylinder. And similarly, if I just, the same thing, if I had an electric field going along the cylinder in the z direction, and I flipped the direction, it would flip the direction of that electric field. So also, no Ez, which would be along the cylinder. So that tells me that my electric field for the axial case, the only thing it could be is away from the cylinder, because if I had this thing going this way, and I reflect it, then it would be going away on the other side, right? If this were coming out here and I reflect front to back, it would be going out the back. That is allowed. That would look the same as long as it's going, reflect. Those will swap directions. It'll be fine. If I reflect top to bottom, I've got this, reflect top to bottom, it'll look fine. So only, my electric field is only, I'll call it E sub s times s hat. Away or toward the axis of the cylinder. And that's why we call it an axial symmetry, because the electric field only points toward or away from the axis. More than that, though, for coordinate dependence, how does this depend on where I am? We've got the direction of the electric field limited now, but how does this depend on where I am? If I slide along the z direction, if I slide back and forth along z, you'll find that translations sliding along z means that we are independent of the z coordinate. And if I rotate around that z-axis, we'll find that means, because rotating doesn't change the cylinder, that tells me that we are independent of the angle phi that we are around here. So it's only a function of s. The only coordinate left is s, and so we find that our electric field in this case, my electric field equals E sub s is a function only of s hat. Again, symmetry has gotten to this point where we have a very simple case, and where we have a very, very simple result for what that electric field can look like. It's a function of just one coordinate, which makes Gauss's law much easier to work with. Finally, the last case that I want to look at, the last case to discuss, is the case of radial symmetry, and of a radial electric field. And here, this is the one case that has an actual sort of familiar situation, and something you can actually make instead of you can actually make something with this symmetry instead of just approximately the symmetry. This is the case that corresponds to spherical symmetry. Spherical symmetry. So I'm going to just have some spherical distribution of charge, and by the way, a single point counts as a spherical distribution. If it's a single point at a center of some sphere, that's a spherical distribution. And if I have a perfectly spherical distribution, what that means in particular is that I can rotate around the center any which way, rotate that sphere any way I want to, and the charges will look the same. The natural coordinates to use for talking about spherical symmetry are spherical coordinates. Spherical coordinates r, theta, and phi, where theta is the angle down from the North Pole and phi is the angle around the equator. That's the physicist convention for spherical coordinates. We're going to stick with it. And so that's spherical symmetry, and we can use our reasoning again, use symmetry reasoning to figure out what's going on. The symmetries we have are all rotational symmetries. So in particular, we can use some of the same arguments we did before to say that if I had some electric field going at any sort of arbitrary direction around here, if I rotate, it has to, the whole field configuration has to match. So fields pointing away from the sphere will look the same if I rotate it around, but a field pointing around, for example, if I had a field that was pointing around the sphere and I rotate it around to here, it's not going to look the same. It's going to go the other way. So by just rotational symmetry, rotations around the center, that set of rotations limits us then, because we have that rotational symmetry, that tells us that we can't have any theta or phi directed fields. Any field coming down like this, it comes down like this, if I were to rotate around, it would be going up instead. So that means that it can't have those things. So we only have, my electric field is only radial. E sub r hat, hence the radial name. And just as before, rotations around here, because it can't depend on what angle I'm at, if I rotate it, it can't change anything. That means, same idea, rotations around the center tell us that that function, that E sub r, the strength of my field, can't depend, it has to be independent of theta and phi, independent of angle. Again, this is just spherical symmetry. If I have something, if the charges are independent of that, then rotating the sphere can't make the charges look any different, and that means the electric field can't look any different. So in this case, my electric field vector for this case winds up being r component, only a function of r hat, pointing straight away from the center. This r hat is the vector, or is the unit vector directly away from the center. If E sub r were a negative number, it would be straight toward the center. But that tells me that I've used symmetry to get myself from a general electric field to an electric field that only depends on one coordinate and only points in one direction. These are really powerful results. These are great results, and you can see where these names come from. Unidirectional, only z hat; axial, only away from the axis; radial, only away from the center, the radius of the sphere. You can see where those names come from. Each one is a function of only one variable, so Gauss's law will turn into a statement about ordinary calculus instead of multivariable calculus, and we get to use it easily. These are the three special cases that show up for Gauss's law, and I hope that's useful in reviewing how these ideas work. Sorry for stumbling a little bit in arguing the symmetry argument for the axial case. I was a little bit too eager to do rotations and translations in this part instead of that part. So, but in general, this is how you go through those arguments. And again, these things about the way the electric field can point are true just based on the idea that electric fields result from electric charges and nothing else. It's a really powerful statement. I think it's really cool. I hope you do too.